So I talked about backward elimination. That's basically where I start with the full model and then eliminate one non-significant variable at a time until I'm left with just significant variables. The forward selection strategy is the reverse. So instead of eliminating variables, we're going to add one variable at a time until we cannot find any variables that present strong evidence of their importance in a model. So in this kind of strategy, we start with no variables at all. So for the Mario Kart data, my first model would be basically no variables. So my model here would basically be the predicted price is 47.43. So which would be the average of all those auctions that that was included in the data. Okay. Now, so we start with that. Now what we want to do is we want to see if we can add a variable to the model. And what I'll do is I'll create 4 different models and add a different explanatory variable each time. So we fit each of the possible models with just one variable. So model 2 would include just the con_new predictor. Model 3 would include the stock photo variable. Model 4 would be the model with just duration. Model 5 would be the one with just wheels. So there's 4 different models here that we're trying to fit. And yes, there are 4 different models. And each of them will provide a p-value, test statistic. So it provides. So what we want to see is which one looks the best. So you see here, model 2, the con_new. This one looks to be important. Stock photo by itself looks to be important. So your model 4. There we go. Just duration. Looks like all these variables in of themselves, all these variables are important. Looks like 3 of them had a p-value of about 0. So we want to use is we want to go ahead and look at the test statistic to be the tiebreaker. And of the 4, it looks like wheels had the largest test statistic. Notice of the one farthest away from 0. So going back to the previous 2, we had 8.66 and 2.41, negative 4.76, 15.6. Okay, so of these, in and of themselves, if I just look at one variable, all of them were important if that was the only variable we looked at. But the most important of these 4 look to be wheels. So that's the one. I'm going to go ahead and add that to my model. I'll keep that permanently now. So out of these 4 variables, the wheels variable had the smallest p-value and the largest test statistic. Since its p-value is less than 0.05, it's actually less like it was smaller than 2 times 10 to the negative 16. We'll go ahead and add wheels variables to the model. So now every model I look at will include wheels. So once a variable is added to the forward selection, it will be included in all models considered as well as the final model. But since we've successfully found a first variable to add, now we're going to consider adding a second variable. So there's 3 new models I have to look at. Model 6 of these models is I have wheels and whether or not in the con_new variable. Model 7 would be wheels and the stock photo variable. Model 8 would be wheels and the duration variable. And here are the results. So the first one, you can see both the variables are important. And see, my con_new was 6.04. Okay. Model 7, both the variables were important, but you notice that the test statistic is not quite as large. P-value is also larger. So Model 6 is preferable to Model 7. Duration, I guess in this case, duration would have been important, but my test statistic is negative 2.56, so is the one that's closest to 0. What that means is I'm going to go with model 6. Wheels is an important variable, and con nu is an important variable. So now I'm going to have both these variables in my model. So of these models, 6, 7, and 8, the model with the wheels and con nu variables had the lowest p-value and highest test statistic for its new value. So the p-value here for con nu was 1.4 times 10 to the negative 8. Now, because this p-value is less than 0.05, we will add it to the model. So now every model I look at from here on will have both wheels and con nu added to it. So now we have fitted 2 variables. Let's see if we can try to fit a third one. So we go through this process in another time. So model 9 would include stock photo, con nu, and wheels. Model 10 would include duration, con nu, and wheels. And here are the results of these two, model 9 and model 10. So you can see in both of these, in this case, stock photo was not significant, so I can just throw out that model right away. Next one, p-value 0.6817. Duration is not important, throw it out. Neither of these models work for us. Both these models have non-significant variables. And so neither of these models work. That means I go back to the previous one, the one with just wheels and condition nu. So the p-value corresponding to stock photo in model 9 was smaller than the p-value corresponding to the model 10. However, neither of these were below 0.05, so there was no evidence that it should stock photo should be included in the best model. So therefore, neither variable is added, and we are finished. So you notice that we ended up with condition nu and wheels as my 2 variables. Those happen to be the same 2 variables I had with backwards elimination. Technically, this is not always going to be true. Forward selection and backward elimination don't always end up with the same answer. The backward elimination strategy begins with the largest model and eliminates the variables one at a time until we are satisfied that all remaining variables are important to the model. The forward selection strategy starts with no variables and adds one at a time until there are no more important variables to find. So there is no guarantee that backward elimination and forward selection strategies arrive at the same final model. It is worth noting there is also no guarantee that either strategy will arrive at the overall best model, especially when there are hundreds, thousands, or even millions of variables to check. Fortunately for us, we're only going to look at models that have a few variables. Now, one reason, in terms of why forward selection and backward elimination don't always get the same answer and don't always guarantee you get the best answer, the reason is just there's just too many models to check. Just for some reference, if you have 50 variables, if you could check 1 million models a second, it would still take you about 36 years to look at 2 to the 50th possible models. Basically, for every additional model is basically 2 to that number of variables is how many models there are possible. So if you're looking at 1 million models a second, it would still take you about 36 years. If you had 100 variables and you happen to look at 1 trillion models a second, it would still take about 40 billion years to check all possible models. So have fun with that. Essentially what I'm trying to say is that it is impossible to look at every possible model, so it's impossible to guarantee that we have the best overall. So it is often impossible to consider all possible models. So the best model cannot be guaranteed. Fortunately, backward elimination and forward selection will generally give us pretty good models to use. Now, if backward elimination and forward selection strategies are both tried and they arrive at different models, choose the one with the larger adjusted R squared as a tiebreaker. You can find a lot of times you'll find the adjusted R squared on the table. The examples I've had before, it was in the lower left. Basically, the larger that R squared is, the better the model is. So it's generally acceptable to use just one strategy, either backward elimination or forced selection. But using both is also another way of kind of guaranteeing or checking possible ultra-optimal models.